you know. You may know that I've been a frequent visitor to Bangladesh, and several times, 5 times I've visited there, and Bangladesh is on a delta. The highest peak in Bangladesh is like 200 feet. And I went and met with women borrowers of the Poverty Lending Bank, the Grameen Bank, and got to interview women and talk to them about their lives. And, you know, very inspiring about how they were turning their, you know, climbing out of poverty with the use of a tiny loan. And these women have never owned a car. They've don't have a refrigerator. They've never had air conditioning. And yet they're already suffering from effects of our changing climate. So, and I can't imagine what it's going to be like. And of course, what we do is going to matter. But in any case, the way you deal with things is taking action in a constructive way. And one guest I have here is Dave Fallon. Please, Dave, please stand. Dave is head of the local chapter of Citizens Climate Lobby. And if you're interested in doing something constructive about the situation, please see Dave afterwards at the front of the screen here. And he's got a few brochures on your way out too, if you'd like to participate. Thanks. Well, our guest today is Dr. Robert Davies, and he is a science communicator. Now, I know that maybe more than a few of you would rather he talk about how to spy on their friends with their microwaves. You'll have to leave that to another day. Dr. Davies has been an associate of the Utah Climate Center and is adjunct professor at Utah State University's Department of Plants, Soils, and Climate. He lives and works in Logan. He has served as an officer and meteorologist with the United States Air Force. He worked for NASA on the International Space Station project and taught on the faculty of 3 universities. Scientific work has included research into interactions of spacecraft with the space environment, the fundamental nature of light and information, and the Earth's changing climate. For the past decade, Rob's work is focused on communicating the critical science of climate change and sustainable systems. His fascination with science began as a child growing up in the Black Hills of South Dakota. And he writes the following: "It was born of this landscape around me, mountains, caves, and canyons, badlands and dinosaur bones, granite spires and dark midnight skies. Summers were spent hiking Lookout Mountain and Spearfish Canyon. Winters were spent skiing nearby mountain peaks. I gazed upward through my grandfather's telescope, watched in awe the fearsome power of high plains thunderstorms, and pored over the World Book Encyclopedia that occupied 2 shelves of the living room bookcase. It was also a childhood filled with theater, literature, and music, telescopes, microscopes, and math competitions. Newton blended seamlessly with Shakespeare, Einstein with Seneca, Darwin with Vonnegut. I'm not sure I distinguished at the time between scientific endeavor and artistic endeavor. It was all just human endeavor. And I still feel that way today. So we're in for a real treat today. Please welcome Dr. Robert Davies.
One never knows where they dig this stuff up. Well, thank you all for coming today and taking time in your day for this invitation. I am quite honored to speak to the group with such a long history of devoted community service, both local and internationally. So thank you. So as Scott mentioned, I worked for a while on the International Space Station. I was a technical and scientific liaison for NASA in Moscow. And I spent a lot of time wondering, thinking about what it would be like to live and work on this station. You know, just sort of life stripped of all accoutrement. You eat, you work, you sleep, you exercise up to 6 hours a day. The astronauts. In this environment, and all the while, the vacuum of space is just a few inches away, this hard boundary between survival and non-survival. And I used to imagine all kinds of scenarios. In fact, that was my job, was to imagine different scenarios and make sure that the crews had procedures, roadmaps to guide them if some of these scenarios came to pass. And one scenario in particular, I still find myself thinking about quite often, and it goes something like this. So it's a regular day. The crew gathers in the laboratory module for the morning briefing. And when the discussion comes around to the science officer, she says, you know, I've been looking at the data, and I think there's something wrong with the life support system. In fact, I'm sure of it. You can sort of imagine the scene as everyone's looking at her, and they're looking at each other, and there's a silence, and a pretty quick realization. And then the commander says, in that sort of a Masters of the Universe astronaut, you know, Houston, we have a problem, measured way, right, everyone, today we have a new top priority. And they get busy. And it's not too hard to understand why I might bring that up today. It's a near perfect analogy to the situation, stripped of all, down to its essence, in which all of us here on Earth find ourselves today. The scientists have been coming to the meetings every morning for several decades saying, you know, we've been looking at the data, and we think there's a problem with the life support system. And in fact, we're pretty sure. But unlike the space station, this spaceship doesn't have a commander. And up until now, yet, we haven't had that moment of silence. Everyone looks at each other and then decides to get busy. The message just isn't really penetrating that quickly. And so that's what I would like to spend the rest of the time talking to you about today, is this message about our life support system, and in particular, our disruption of the entire planetary climate system, and the level to which this message is penetrating today. Now, it would be helpful to divide the conversation into two pieces. We've got the science of this topic of climate change, but then again, there's the public issue of the topic as well. Now, the science, of course, is about the observations, the measurements, analysis. It's about what we know about Earth's climate system and how it's changing. The public issue, on the other hand, brings into account other things: our culture, our identity, our politics, our economics, who we see ourselves to be. In short, it's about how we respond, how we choose to respond to the knowledge that we possess. I'm going to start with the notion of what we know. We're going to talk about both of these, but before we can talk about how we respond, we need to be on the same page about what we know. And not just in this room, but in the society. And so, let me start by saying that understanding Earth's climate system to the level that we do is truly one of the great scientific achievements of humanity. It is built upon an enormous spectrum of science, a huge amount of science, many scientists, sitting at the very tippy top with subdisciplines and sub-subdisciplines. And certainly while Earth's climate system is incredibly nuanced and intricate, understanding the change that's happening and why, distilled, is really quite a simple story. And so what I'm going to do is tell you that story. It comes in 4 chapters. I think I can do it in about 15 minutes. So somebody time me. We'll see if this works. And the first thing we know with very high scientific confidence is that Earth is warming globally. Okay? This is what it looks like from the end of the 19th century to the middle of the 20th to today.
Wow.
And we're going to look at this one more time, and as you see the different locations on the globe change from the cooler blues to the warmer reds, that is those locations warming up. And the more the change, the deeper the red, the more the warming. So here's again, from the end of the 19th century to today. Now let me be clear, this is temperature change, not temperature. The North Pole did not get warmer than the equator, but it has warmed up more. And you can see a couple of things from this data. First, the entire globe is warming. That's very clear. And second, that warming is not uniform. The high northern latitudes are warming faster, and land is warming faster than oceans. We understand why that should be. However, if you average it all up, it turns out the planet's warmed up just over 1 degree Celsius in the last century or so. And for those of you who are metrically challenged, you can convert a temperature change in Celsius to a change in Fahrenheit by roughly doubling it. It's about 2 degrees Fahrenheit. I'm going to put that number in context in a little bit. We can also do that for every year over the last 130 years or so and measure a temperature change relative to some baseline. So that's what this looks like. On the vertical scale, we're looking at a temperature change from a baseline. The baseline is the mid-20th century average, just completely arbitrary, something we can relate to. And here you can really see how it's progressed over the century from the much cooler years in the early part of the 20th century to this continuous progression of record-setting warmth in the late 20th century and early 21st century. Last year was the warmest on record, smashing the previous record, which was 2015, which smashed the previous record before that, which was 2014. So this is what it looks like, and this is what global warming is. This is what we mean. Second thing we know with very high scientific confidence, and again, not to put too fine a point on it, is why the planet is warming, and specifically it's because of us. More specifically, mostly from the emissions of greenhouse gases, carbon dioxide being the most important of those. And this is important because carbon dioxide is now, as a result of our emissions, building up in the atmosphere. This is what that looks like. It has built up over the last 250 years or so by an amount of about 50%. 280 parts per million to where we are today, about 400 parts per million. A little more than that. That has come mostly in the last 40 years or so, 50 years, which I've demonstrated here, which I've depicted here. And this is important because carbon dioxide is a greenhouse gas. Now, greenhouse gases, I'm sure you've heard of it, but let's review, are able to, because of their molecular structure, absorb light energy that is leaving the Earth, mostly infrared. So light that we can't see, but it's light nevertheless, and convert that energy into thermal energy in our atmosphere and at the Earth's surface. In other words, energy that used to be escaping the planet is now trapped, and as a result, it's warming up the planet. This is very well understood physics. We've understood it for more than a century. And so that's the short answer. This is what's causing the warming that we're seeing today, and in particular over the last century or so. The third thing we know with high confidence is that this human-produced warming of the planetary system is disrupting the entire climate system. Everything is connected in the climate system. So, for example, we know that warmer air will hold more moisture. And as a result, evaporation intensifies. And so areas that are dry tend to become drier. At the same time, though, this intensified evaporation means there's more water vapor in the air. And so when you get a storm, there's more water up there to come down. And so you get more intense precipitation as well. This is what we call an intensification of the hydrologic cycle, the water cycle. And if this were the only impact of global warming to the climate system, it would be significant. We see this happening on a global scale. It's a signal we've been able to detect for more than 40 years, this intensification of both evaporation and precipitation. But that is not the only impact. As I said, everything is connected. So when you change the temperature, you change everything else. You change where storms occur. You change major storm tracks, which are in the northern mid-latitudes guided by the jet stream. You change the behavior of the jet stream, the weather patterns. So where it rains, where it doesn't, how much it rains, where it snows, where it doesn't. You change where things can grow and where they can't. Where things can live and where they can't. You change sea levels, sea chemistry, soil chemistry, river and water chemistry on land. You change everything else. And so that's what we mean by global climate change. Okay. So Of course, when you change the physical climate system, you change the biosphere, all the collection of living bits on the planet, and the biosphere is currently being impacted quite significantly across the planet. Species are migrating away from the pole, away from the equator and toward the poles and upward in elevation. We see a very pronounced effect in our ecology here in Utah as a result of the mountains. Some species are going extinct. Some species are changing their habitable range. The ones that can move fast enough are, those that aren't are dying off. And then, of course, we change the physical climate system and the living system. Within it, you change that one piece of the living system, oops, which I call the anthroposphere, the collection of all the human bits on the planet, us. And human systems are indeed being impacted, from water systems to food systems to health systems to political systems as well, with the change that we've already seen. So this is what we mean by climate change. Now that's kind of on a broad scale, a general scale, a global scale. All of this is taking place on a smaller, much more local scale here in Utah. Every place in Utah is warming. Hopefully you can see a little bar at the ends of those graphs going upward. The blue bar is the temperature trend in those different locations over the last 40 years or so. Every place in Utah is warming. As a whole, Utah is warming at about twice the global average. So we've warmed about 4 degrees Fahrenheit in the last century. And it is impacting us locally. We are seeing certainly higher average temperatures, but also higher extreme temperatures, a measurable decrease in the snowpack. We're seeing impacts to our ecological systems, for example, bark beetle infestations that are wiping out large stands of trees, contributing to hotter and bigger wildfires, and the list goes on and on. But we are seeing these now measurable impacts rising out of the noise of natural variability. I want to look at 2 of these real quick. These extreme high temperatures. I'm going to show you Tooele, which has a very nice long temperature record. The people who did the temperature record in Tooele did so quite diligently for the last century or so. And what I want to show you are extreme temperatures in Tooele. So what I've plotted here is a histogram of days above 90 degrees for the different decades over the last century or so. So the 1900s on the left, the 1910s, the 1920s, all the way to the right where you get to the 1980s, 70s, 80s, 90s, and the 2000s. Okay, and you can see that upward trend of more days above 90 degrees, pretty pronounced for the last 40 years or so. It gets even more interesting as we go higher. There's days above 95 degrees in Tooele. 100, so 66 days or so above 100 degrees in Tooele in the entire 20th century. 4 such days in the first decade of this century, and 101, 102, 103, same idea. 4 days above 103 degrees in Tooele in the 20th century, 28 such days in the first decade of this century. In Park City, days below 32 degrees has been dropping by about 6 weeks over the last 6 weeks, fewer days that you can get snow in Park City. And that is, in fact, sort of a representative notion of why our snowpack is decreasing. And that's important, of course, because most Utahns get melting snowpack. So, the planet is warming because of the addition of greenhouse gases to the atmosphere from humans, and this is driving planetary scale changes to the atmosphere. The 4th thing we know with high confidence is that if we continue on the path that we are on, this brings with it extreme risks for humans. Now, how do we know that? That seems like maybe a little bit more subjective. So there are 2 ways that this is assessed. The first is assessing the impacts that we've already seen from the warming and the subsequent climate change that we've already experienced. And what we find is around the planet, no place is exempt from seeing consequences. Some places on the planet today, some people are already experiencing catastrophic impacts. That is already happening on the planet today. Whole island nations in the Pacific are in the process of moving. Some have already moved. Scott spoke eloquently about the situation in Bangladesh, and one can go on and on. But based on calibrating them off of the impacts that we've already seen, and then using models to project, well, where do we think we're going, gives us this conclusion that we are facing some high risks if we continue on the path that we're on. models. So these are not the models that are helping us better understand Earth's climate system. Models in this case is just physics. And regular old physics, not climate physics. This is the same physics that makes microwave ovens, digital cameras that we can put on spacecraft that can take pictures of our planet from the edge of our solar system. An equation that tells me that a molecule of carbon dioxide will absorb a certain wavelength of light and convert it into thermal energy is the exact same physical equation that allows us to build every piece of solid state electronics in this room. It's called the Schrodinger Equation. Well-established physics, applied to the climate system. And what it tells us moving forward is the following. I'm going to give you a thermometer here, 45 degrees, calibrated in Fahrenheit, you're welcome. On the left is the global average temperature at the depth of the last ice age. Let's call it about 12 or 15,000 years ago. On the right, 75 degrees Fahrenheit, the warmest we think the planet's ever been, about 55 million years ago. The green oval is where humans in the human ecosystem have always existed. Modern humans coming on the scene about 200,000 years or so ago, the anthropologists tell us. So this is the human climate in the green oval. Between the two lines is the climate in which civilization arose and has always existed and to which it is exquisitely adapted. Shorelines, areas where you can grow, areas where you can find water, habitable versus uninhabitable. The purple is the range of projections where we're headed by the end of this century, in the next, let's call it 80 years or so. And you might say, well, that's quite a range. This is all to scale. An additional maybe 3 degrees Fahrenheit, all the way to an additional maybe 12 degrees Fahrenheit or 13 degrees Fahrenheit. You might say that's quite a spread. The models don't seem to be doing very well. But in fact, the reason that the spread is so big is because you have to calculate for different scenarios. And while there's some uncertainty because we don't understand the physics of the climate system perfectly, most of the uncertainty comes because we don't know how we will choose to move forward. So the low end of those projections are for what we call low carbon emission scenarios, where we begin to get a handle on our carbon emissions and bring them down reasonably quickly in the next several decades. The high end of those projections are for high carbon scenarios, where we continue on a business as usual pattern of producing greenhouse gases. We are moving in the process, even on the low end of the spectrum, to a new climate for humans. We're doing so very, very quickly. It's already brought with it some serious impacts, and we can expect serious impacts. That said, the difference between the two ends of this spectrum are very big. So let me give you an example of how this works as we move forward. Here's some temperature projections for North America. On the left, a low emission scenario, a low carbon emission scenario shows an additional 4 degrees Fahrenheit across North America or so by the end of the century, leveling off by the late part of this century. On the right, the trajectory we're currently on, a high carbon emission scenario, an additional 13 degrees Fahrenheit over much of North America. The deep red in the north there is about 25 degrees Fahrenheit warming. And by the way, that doesn't level off at that point. And we continue to warm for another century or so. That's just where we cut it off for these simulations. That level of temperature change is extreme. This is some projections of snowpack here in Utah. So I'm going to have you look right here. This is springtime snowpack, March, April snowpack, when it's at its deepest, ready to start melting and fill our reservoirs. The darker blues are deeper snowpack. The white is thin snowpack. We're going to start with some observations in 1950. And you'll see that snowpack is variable. We all know that. Some years are snowier than others. As we move into the 1980s, the variability gets bigger, though. That is a signal of the changing warming climate. And now we're moving into projections under a high carbon scenario. You see continual decline of the snowpack through the middle of the century. And then by the latter half of the century, our springtime snowpack essentially disappears. It's not a difficult case to make or to understand. As the temperatures warm, more of our precipitation comes as rain rather than snow. And we've already seen that signal emerging, as I mentioned. One more projection I want to show you is for soil moisture, of course, incredibly important for our civilization, among many other reasons. I'm going to show you two scenarios. One is a moderate carbon emission scenario. We're sort of getting religion, so to speak. Substantial drying through the middle of the century continue drying through the end of the century, but starting to level off. As the areas get browner, they're getting drier. As they get bluer, they're getting wetter. Now under a high emission scenario, again, what we're currently tracking on, drying through the middle of the century and then dramatically intensified drying through the end of the century. Now I haven't really given you numbers in which to interpret this. I'll simply tell you that the people who study this, the agricultural scientists, the agricultural economists, the social scientists, tell us that the scenario on the left is dangerous and the scenario on the right is catastrophic. And the term catastrophic is used technically to mean not adaptable. Not adaptable. Under the scenario on the right, you essentially can't, agriculture as we understand it in North America, particularly the lower 48 of the United States, is not really possible. That is the trajectory we're currently on. Now, I've given you quite a lot of, just a number of pictures here, temperature, precipitation, snowpack, that sort of thing. I just want to help you put this into context in the few minutes that we have. This is Lonnie Thompson, an eminent glaciologist at Ohio State University, who says virtually all climatologists are now convinced global warming poses a clear and present danger to civilization. At this point, I should interject that I almost never get invited to parties anymore. This is Kevin Anderson, quite an eminent carbon modeler. There's a widespread view that a 4-degree future is incompatible with an organized global community. By 4 degrees, he means global average warming of 4 degrees Celsius above pre-industrial temperatures. We've already warmed about 1 degree. That such warming is likely to go beyond adaptation is devastating to a majority of ecosystems and has a high probability of not being stable. What he means by that is somewhere between, say, 2 and 4 degrees, the climate, paleoclimate evidence from past climates suggests that the climate system is unstable. You pass a certain tipping point and you're going to run off to a very different climate state with no chance really of recovery in any kind of a human timescale. So 4 degrees isn't where it ends, but somewhere around there, 3 to 4 degrees is where those tipping points we suspect lie. So these are quotes from 2 quite eminent scientists. There are dozens and dozens and dozens, probably hundreds of such quotes I could have pulled from the popular press and increasingly from the scientific literature, which is almost unheard of for these kinds of assessments to be showing up in the actual scientific literature, and yet they are. I will just tell you that this is the mainstream scientific assessment of the situation that we're in. So there's our story. How'd I do? Did I get it done in 15 minutes? Earth is warming because of us, principally the emission of carbon dioxide into the atmosphere. It's driving a disruption to the planetary climate system, and it brings with it extreme hazard for humans and the human ecosystem and human civilization if we continue on the path that we are on. So having told this story, quite a lot of questions arise in the thinking mind. And the first one is, we're facing this risk, how do we manage it? And the science has something to say about managing this risk. In fact, the equation for doing this is pretty simple. More carbon equals more risk. And so what we can try to do is identify a dangerous line of warming. Now, this is an imperfect measure, but it's one that has been largely accepted by the scientific and global international community as trying to get a handle on where are we and what should we try to do. And that line, a couple of decades ago, was set at about 2 degrees Celsius. Remember, we've already warmed a little over 1 degree Celsius. Saying that beyond that, we believe the risks of extreme impacts go up dramatically. Of course, we don't know exactly where the line is. But based on calibrating to again, the impacts we've seen over the last several decades from the warming that is ongoing, last year that danger line got reassessed to about 1.5 degrees Celsius. I'll come back to that. But based on some danger line, and we're going to go with 2 degrees for the moment because that's what we've run the models for, you can calculate a carbon budget. How much more carbon can we dump in the atmosphere and maintain some kind of a reasonable chance of staying below that amount of change, of warming. So we can calculate that budget, and keeping in mind that the danger line has been lowered. We're still going to stick with 2 degrees for the moment. Here's our carbon budget for 2 degrees. Remaining carbon budget. Here's how much we can dump into the atmosphere. About 1,000 units of carbon dioxide. Gigatons for those of you interested. Think of it as 1,000 units. But these calculations were done 7 years ago. These model runs were done 7 years ago. So we burned through some of that. So there's our remaining budget. And on our current pattern of consumption of fossil fuels, this is how quickly we're going to burn through that budget. About 2 decades, a little bit less. If you want to go with the 1.5 degree carbon budget, we're going to burn through it in about 8 years. And here is that carbon budget relative to our known carbon reserves. This is coal, oil, and natural gas that we've already found and we're already exploiting. We're already developing. So in other words, the physics tells us that we can burn about 1/3 of our known traditional reserves, coal, oil, natural gas, from the standpoint of risk management. Now, I should mention that the metric that was used here is 2 times out of 3 you stay below that temperature rise with this budget. I don't find that particularly good risk management, considering the scale of the risks involved. That's 2 bullets in a 6-shooter playing Russian roulette. But nevertheless, that's the standard that was used. However, we have, in the meantime, been developing what are called non-traditional carbon reserves. This is things like hydraulic fracturing and tar sands recovery. So we should include those reserves as well. And if we do, we find that our budget is only about 1/8 of our existing identifiable reserves that we are currently exploiting. So this is just the physics. This is not the politics or the sociology of any of this. This is just what the physics tells us constitutes meaningful risk management in this situation. Okay, so here's the summary. Dangerous climate disruption, which means 2 degrees Celsius, is currently underway. Catastrophic, meaning 4 degrees or larger, disruption is probable this century. And we've got about a 2-decade window, though, for meaningful response. And I find this good news. The good news is that where we go is still largely in our control. The physics suggests it's not going to be there for very long, maybe a couple of decades, but for the moment, it is still within our control. I want to do one more thing. These are the things that we know with high scientific confidence. This is the scientific story that we are able to tell. When I say we, I just want to be clear. I mean the world's climate science community, which is an extremely large community of well-trained, sincere scientists, many thousands of which. I will simply tell you that every relevant scientific organization on the planet concurs with the story I just told you, and has issued explicit public statements to that effect. This includes the US National Academies of Science, every National Academy of Science in the world, prestigious organizations like the American Association for the Advancement of Science, the American Chemical Society, the American Meteorological Society, the American Geophysical Union, the list goes on and on. There are no dissenting scientific organizations. In fact, the level of consensus among the individual scientists has actually been studied by more than a dozen different studies, all of which converge on the same answers. Roughly 97+% of the active publishing climate scientists who are studying this, thousands of scientists, concur with these conclusions that I presented to you. In my mind, this is the reason that we as a society take this science seriously. It is based on a mountain of evidence, many independent minds giving us these conclusions, like many witnesses to the same event telling us essentially the same story. Okay. So that's what we know. One moment. How do we respond? Let me close with these thoughts then. So I was told in my preparation for this talk that this was and I quote, a savvy group, and you want to hear about solutions. I'm very pleased about that. Here's the solution. We have to decarbonize our global civilization. Developing nations need to do so by 2035, developing nations by 2050. That's the science. That's the solution. Now the roadmap to getting there is a little more complicated. I will say that progress is being made. An awful lot is happening around the world. Last year, we got a comprehensive international agreement signed by nearly 200 nations to start bringing down our carbon footprints. Some nations are making pretty good progress on this. Great Britain has now reduced its carbon emissions to a level not seen since the 19th century. Much of Europe is making good progress toward decarbonizing. Even China is now aggressively moving away from fossil fuels, planning their route to do so. Here in the United States, it's happening very locally. Salt Lake City has made tremendous progress. We now have 3 communities in Utah that have committed to becoming carbon neutral by the year 2035, Moab, Salt Lake City, and Park City. Logan is in the process of debating and probably passing a resolution to be halfway there by the year 2032. Lot is happening at the local level, and even at the regional level, California probably being the single largest example. But what I really want to say to this audience, if you want to find a way to be relevant on this topic, you certainly can. If you spend 30 minutes on the internet tonight, you'll be well on your way. I was given 25 minutes today to make my case, and there's one more point I want to make. From my perspective, I've been doing this for 10 years now. I was a physicist. I was happily ensconced in my laboratory in England, as it happens at the time, 10 years ago, doing something called quantum optics. And I chose to do this for a year. I thought, I'm going to do a one-year public service sabbatical on climate change communication because I think we need it. And here I am 10 years later. So I don't think I'm going back to the lab. We have the technology to do what we need. We actually have the roadmaps to do what we need, technologically. What we don't at the moment have are societal roadmaps, sociological roadmaps, what I call the harder sciences, the social sciences. I can state unequivocally that the response to date is at a pace and scale that is wholly inadequate to the risk. We have not as a society properly mobilized to do it, and we haven't done that because we as a society are not yet having a coherent discussion on this topic. We're not having that discussion because one whole segment, in particular our government, will not accept the premise that this is happening. Imagine if you can the following scenario in, say, Miami. It's discovered that the Zika virus has made its way to the city. Its city's leaders and citizens come together to discuss what's to be done. They talk about quarantines, mosquito abatement, public awareness, information campaigns, free health consultations, screenings. All of these are put forth and debated. And a new course of action is set and implemented. This actually happened last year in Miami. All of the decisions weren't popular, but they were able to contain the outbreak. Difficult decisions were made, and not everyone was happy, but no one, I will wager, came to those meetings to suggest that no such disease as Zika existed, or that Zika was not caused by a virus or transmitted by mosquitoes, or that the disease posed no threat to the community, and in fact might even be good for us. Yet that is the exact situation we find ourselves in our public discussion on this topic of climate change today. A significant section of our country will not admit to the problem existing, and until we have that, we cannot have a coherent discussion about how to meet it. And while we are having individual coherent discussions in certain communities and in certain places, those efforts have gone about as far as they can, in my opinion. They're making good progress, but it's not fast enough. And so if you want to make a difference, particularly this group, on this topic, I will put this forward. We have to be able to have this conversation. And it can no longer be socially acceptable, particularly for policymakers, to deny the existence of this problem. We can have the debates about how to go about addressing the problem, but we can no longer have the discussion about, does this problem exist? We do not have the time for it. That's come and passed. Here in Utah, the legislature passed for a second time on the opportunity to simply pass a resolution that climate change is real. In fact, they passed a resolution in 2010 that says climate change is not real. This can no longer be acceptable. We can no longer simply agree to disagree. My ask for all of you today is that when you have the discussions with your colleagues, with your business partners, with your friends, with your family, and in particular with our policymakers, it is not okay when they deny the existence of this problem, particularly with the policymakers. Holding us up. Thank you for your attention, and I'm happy to answer any questions, and I'll stick around. I understand most of you have to leave quite soon, but I'll stick around for as long as you have questions. There was one, yes, ma'am.
You know, a lot of us are trying to do everything we can to reduce our carbon footprint, and as we're talking or speaking with people that may be climate change deniers, there is always that rain. Well, look, it's raining a lot. Can you give that? You gave the explanation why there is more rain. Can you give me the one sentence response that
Why there's more rain?
Yes.
Warmer air holds more moisture.
Okay. That's what I need.
Yes. Sir.
What percentage of the contribution to the CO2 emissions does the United States have versus the global contribution?
Between 15 and 20%.
So we could do everything and we're still 75, 80%, 90%, dependent on the other countries doing the same thing.
We have that agreement in place. Every other developed nation on the planet is making faster progress than the United States. The world's problem is not the rest of the world. The world's problem, frankly, right now is that the nation that considers itself the leader of the world is not at the table in a meaningful way. Sir?
When you get in people that say that the environment naturally changes, it goes through its cycle. Can you talk about how we can determine the difference between the CO2 and the natural cycle?
Right. So come talk to me afterwards. I'll be happy to take you through the physics of it. But and we'll end with this question. What happens is in this discussion, specific scientific points get brought up. Climate always has, first it's changing, always has, always will. Or it's the sun, or humans couldn't possibly affect it. In my opinion, your answer to this, my answer to this, is not that you understand the detailed physics. It's that a very large, well-trained, sincere community of scientists has been studying this for many decades. Not surprisingly, those questions have come up. Is this natural? Is this the sun? Is it part of some natural climate cycle? The data on this is overwhelming. The answer is no, it's not a natural cycle. In fact, humans are responsible for 100% of the warming that's happened in the last half century. 70% of that is from carbon emissions. Responsible for all of it, 3/4 of it is from carbon emissions, okay? And the reason that you are going to behave as though that's true is not because you understand all of the physics. And sure, ask the questions. Well, I'll take you through it. The reason I think we as a modern society behave as though that's true is because a very large expert community is telling us that that is true. If you would flip it, assume that 97% of the climate scientists say there's no problem, and that none of the relevant scientific organizations think that there's a problem. In fact, they've issued statements saying there is no problem. But 3% of the scientists out there, the same 3% who today just won't accept it, are saying, no, we've got an emergency. And now ask yourself, would I still trust that 3% and behave as though there were an emergency? I think the clear logical answer is no. We need to move forward from a standpoint of risk management. And from a standpoint of risk management, the scientific questions are good, they've been asked and they've been answered. Okay, thank you. Thank you for your attention. And I'll stick around before you do that.
Thank you, Rob, for your speech today. It started a conversation among us. It certainly will not finish with your breathless ending here. We have plenty more to talk about. Our book that we will be donating to the Franklin School, and our guest speaker will sign in the book so they'll know where it came from, is Water Rolls, Water Rises,